Okay, picking up where we left off on intermolecular forces. We've covered one force so far. Our second force is on the screen. Who remembers what our first force is? Dispersion forces. Our first force was dispersion forces. And dispersion forces exist in, where is it? All molecules. Anything that has electrons has dispersion forces, at least to some extent, even if it's a very, very small extent. So it's present in all molecules and atoms. This is our baseline force, the dispersion force, the London dispersion force, the London force, whatever you want to call it, all of those work. And it has to do with electrons, which I represented as blue dots here, just randomly being unevenly distributed. Here in helium A on the far left side, it is shown as evenly dispersed. So they're kind of balanced out within the atom. And then in this middle frame, just randomly, the two electrons happen to be on the same side of the helium atom. And so the right side is a little bit unshielded. The nucleus can exert its positive force past where it would normally be able to because there's no electrons to cancel it out. The electrons, since they're both on one side, have overpowered the positive force, at least to some extent, because they're closer to the edge of the atom's radius. So there's a partial negative force over here because the electrons have gotten together. There's a partial positive on the other side because there's no electrons there. And that can pull over electrons from a neighboring atom if there's a neighboring atom. For helium, helium's almost always a gas. Anytime it's above 4 Kelvin, essentially, it's going to be a gas, so that's most of the time. And so these electrons, this helium atom would have to be right next to it. It would have to be close enough for the partial positive force to influence the electrons here. So even if this has an instantaneous dipole, it might not do anything because it's not always there. So when it bumps into another atom, it might have sorted itself out and now it's evenly distributed, so it doesn't have a chance to exert that instantaneous dipole. But if there is something close, then it can pull some electrons over, and then you've got a really weak temporary magnet force that's holding these two helium atoms ever so slightly together. This would be sort of like if you tried to stop a car that's driving past you at 25 miles an hour, you can just kind of stick your hand out and like wipe it along the paint on the side of the car. That's the sort of force that we're talking about. It's like, really, it's not that much, especially for helium since it's so small. This force does get bigger based on, so the magnitude does get bigger. It depends on how easily the electrons can be polarized, and that depends on the size of the electron cloud. So more electrons are going to cause it to be more easily polarized. So thinking down and to the left on the periodic table, those are going to be larger atoms. Those are going to tend to have stronger dispersion forces. And molar mass, if we're looking at a similar family of elements or compounds, molar mass also scales at the same time that dispersion forces scale. So the example that we looked at, one of the examples, was our noble gases. Our noble gases are a family or a group. And so as we move down the periodic table, the molar mass also increases. And so the boiling point increases. Boiling point, melting point are both related to the strength of the intermolecular forces. So seeing a higher boiling point with something like xenon means that it's got stronger intermolecular forces than helium or neon, for example. And then we've got our second force the second. And force number 2 is the dipole force. Do we remember what a dipole is? Di is 2. Poles like north and south, like on a magnet or like on the globe. So a dipole interacting with another dipole. So 2 dipoles, and again, we're thinking magnets here, interacting. The magnets that we're dealing with here are atoms or molecules. In this case, it's got to be molecules. So the dipole-dipole force exists in all polar molecules. So polar is our focal point for the dipole-dipole force. If we have a polar molecule, then we have the dipole-dipole force. Polar molecules have permanent dipoles. They have permanent partial positive, partial negative distributed across the molecule. And so we get an attractive force between the positive end of one permanent dipole and the negative end of another. So this is between two molecules that are close to each other, two molecules usually of the same thing, close to each other, the positives and negatives can find each other, they can be attracted to each other. So whereas all molecules have dispersion forces, polar molecules on top of that also have dipole-dipole forces. This is a second force we're layering on top of our first force. Polar molecules have higher melting and boiling points relative to nonpolar molecules of similar molar mass. Adding dipole-dipole force increases melting point / boiling point because the intermolecular forces are stronger. The dipole-dipole force is also just stronger than the dispersion forces. So they are even stickier. They're not just putting your hand on a passing car and hoping that you slow it down all the way. I've got a piece of Gorilla Tape on my hand, and I'm going to tag along for the ride with you because this Gorilla Tape is going to set immediately, and then you're just going to be dragged along the side of the highway on the car. So this is what the dipole-dipole force might look like in action. We've got formaldehyde. We know that formaldehyde is polar because we've got carbon in the middle. Carbon's got an electronegativity value of 2.5. Oxygen has a value of 3.5. And so our difference in electronegativity here between the oxygen and the carbon is 1. And that is well within our polar bond range. Our polar bond range being from 0.4 to 2.0 for polar. So we've got a polar bond here. It's not offset by the hydrogen bonds. Those are actually lower electronegativity values. These are 2.1s. Not really the focus here. So if we were to do all the little arrows, it would look something like this. And we can see that the arrows generally are pointing the way that we've got shown as up here. So we get a partial negative on the oxygen, partial positive towards the hydrogen carbon side. And so we've got a permanent dipole across formaldehyde. So the negative end of one can match up with the positive end of the other, and they sort of stick together a little bit, depending on how fast they're moving. If they're moving too fast, if they've got too much energy, if their temperature is too high, they're going to be moving really fast, and so it's not going to work. This would be a car driving past you at 55 miles an hour, you hit it with your Gorilla Glue hand, and it's just going too fast, and so the glue doesn't have time to set, and so you don't stick to the side of the car running down the highway. If we look at the effect of polarity, so adding in the dipole-dipole force on melting and boiling points, for two compounds of similar molar mass, since molar mass is sort of our proxy for, or our stand-in for dispersion forces, similar molar mass means they'll probably have about similar dispersion forces. So we're basically just looking at what's the effect of the dipole-dipole force. Formaldehyde has What two forces? That's the one that we were looking at on this slide. It's two force. Dipole-dipole forces. What else does it have? Dipole-dipole is an intermolecular force. There's another intermolecular force that it has. It's the one that everything has. I wrote it on the screen. Dispersion forces. So it also has dispersion forces. Dispersion forces. Ethane only has dispersion forces. And because their molar masses are fairly similar, their dispersion forces should be about the same. So they have them. They're about the same, so we're just looking again here at the dipole-dipole force, essentially. If we look at the boiling point, ethane has a boiling point of negative 88 degrees Celsius. You would not want to be out in negative 88 degrees Celsius. You would freeze. Formaldehyde, on the other hand, has a boiling point of negative 19.5 degrees Celsius. So negative 88, negative 19.5. Negative 19.5 is way higher. That means it takes a lot more energy for it to boil. The melting points are also similarly very different. So we've got an about 80 degree Celsius difference between the melting points of ethane and formaldehyde by adding in dipole-dipole forces. So that's 80 degrees Celsius is about going from room temperature to boiling water, just for adding on dispersion forces, or adding on dipole-dipole forces. So we're changing the boiling point by a lot, the melting point by a lot, by adding in this one extra force. The polarity also affects miscibility. So we had talked in a previous lecture about why oil and water don't mix, and that's what we're talking about with miscibility. So miscibility is two things being able to dissolve into each other. The definition that we've got in the slides, the ability of a liquid to mix with another liquid without separating into two phases. Will they form one homogeneous mixture? Generally, polar liquids, things that have dipole-dipole forces, things that have a polar bond and don't pass the two nonpolar express checks. Polar liquids are going to be miscible with other polar liquids, but they will be immiscible. They'll form two separate layers. Like oil and water, if they're mixed with nonpolar liquids. And so we have this phrase that's relevant here, like dissolves like. And what like dissolves like means is that polar generally dissolves polar. The opposite is also true. Nonpolar tends to dissolve nonpolar. An example, if you've ever gotten oil on your hands or on your clothes, maybe if you're doing some mechanic work or you're just messing around under your car, or cooking, I guess, you could also get oil on you. That typically can't just be washed away with plain water. If it's really hot water, maybe, but if it's just regular cold tap water, you're probably not going to wash off your oily hands and your oil stains. You're going to need to use some soap. You might need to use some special soap if you've got like car grease on your hands or in your clothes. You might need to use some special soap to dissolve those oils out of your clothes, off of your hands, for example. Polar and nonpolar compounds are generally not miscible. So chloroform and water don't mix. Chloroform is more dense than water, and so it will sink to the bottom if you have them mixed together, and the water will rise to the top. Oil and water also don't mix. The water will sit on the bottom, and the oil will sit on the top. And the Deepwater Horizon oil spill in the Mississippi Delta created this large plume. You can sort of see it on the slides. This large plume of oil slick in the Mississippi Delta around Louisiana. So there's just lots and lots of oil floating up on the surface. It didn't all stay floating up on the surface. Sometimes it globs up and drops down to the bottom, which is also really bad. So there's a whole lot of remediation that has to go into cleaning up big oil spills like that. This one you can see from space. Thanks, NASA. So if you want to determine whether a molecule is polar, the Book's method. Determine whether the molecule contains polar bonds. It has to have polar bonds to be polar. We talked about this in chapter 7. Determine whether the polar bonds add together to form a net dipole moment. So like drawing in the little arrows pointing towards the more electronegative end. We did that with the formaldehyde. If the arrows don't cancel out, so if it has polar bond, maybe multiple, and they don't cancel out, then it would be polar. We also generally can use the nonpolar express for this class. So a molecule will be nonpolar if both of these conditions are true. If we have no lone pairs on the central atom, it has to be the central atom. We can have lone pairs anywhere else, just not on our central atom. And if the atoms bonded to the central atom are identical or have the same electronegativity. So something like CH4, which has this Lewis structure, has no lone pairs on carbon, no lone pairs at all even, and the atoms that are bonded to the central atom are all hydrogen. They're all CH bonds between a carbon and a hydrogen. So this would be nonpolar. Something like ammonia, on the other hand, has lone pair on nitrogen, which is our central atom. This would be polar. We would also want to check the NH bond is polar. Since it has 4 groups on it, it would have a tetrahedral electron geometry. One of those is a lone pair. So then we've got 3 groups left. It'll be a trigonal pyramidal geometry. For those of you imagining at home, you hit your X pose, you turn that 90 degrees with your torso. You get rid of one of your hands, and now you've got a hand that's like sticking up and out. So these are all sort of like a moon lander sort of situation, which is not helpful. But you can see that they're not all evenly spread out. They're kind of one sticking out to the side. And so all these bonds would be pointing towards the nitrogen. So it'd be like getting pulled across the room. They're not going to cancel out, and so it's polar. 2 examples of going through that in case we've forgotten how to do that. That was just a chapter ago, essentially. If you're confused about polarity, Logan would be a good person to see to talk about polarity. So let's determine whether each of these molecules has dipole-dipole forces. You will have to draw the Lewis structure. I'll give us like 2 minutes, and then I'm going to draw the Lewis structures in. That was approximately 2 minutes. Not in video time, of course. So here are the Lewis structures. For CF4, we've got carbon in the middle with fluorines each having 3 lone pairs. For CH3Br, similar situation, carbon in the middle, 3 hydrogens, and a bromine with 3 lone pairs. And then for HCl, hydrogen bonded to chlorine. Chlorine's got 3 lone pairs. Now that you've got the Lewis structures, in case that was a sticking point, go ahead and come up with whether they have dipole-dipole forces or not. How will we know if something has dipole-dipole forces? What things have dipole-dipole forces? Polar molecules. So we're looking to see, are these molecules polar? In order for them to be polar, sort of generally they have to have polar bonds. That's going to be a little bit misleading for one of our things that we're looking at. If we're looking at carbon bonded to fluorine, the CF bond, carbon has a value of 2.5, fluorine has a value of 4.0. 4.0 minus 2.5, we've got a value of 1.5. That's definitely polar bonds. Fairly strongly polar even. So we need to either think about this in 3-dimensional space or write it out in 3 dimensions and then draw in all of our vector arrows and then figure out, do they all cancel or do they add up somehow? Or we do the nonpolar express. We look at our central atom, which is carbon. Carbon does not have any lone pairs. That's our first condition. So no lone pairs on carbon. Check. Are all of the bonds the same? Yep, all bonds the same. All bonds equal. Check. Those are our 2 conditions for the nonpolar express. So CF4 is nonpolar. It does not have dipole-dipole forces. Because it's nonpolar. For B, this is the one that could be a little confusing. If we look at the bond between carbon and bromine, the CBr bond, carbon is still a 2.5, bromine is a 2.8. Those of you that are quick with it will see that that's only a difference of 0.3. Our cutoff is about 0.4. So not polar, which then would mean that the whole thing can't be polar, potentially. However, if we draw this out, I'll do it this way. So on the left, we've got a bond that's in the plane of the board, so it's flat. On the right, the one in the front, the lower one here that I just drew in, that one's coming out of the board towards us. And then the other one back here is going into the board behind us. So thinking of this as sort of like a tripod with 3 hydrogen legs. And then on top, we're drawing the bromine. This is about what the actual shape would look like. And if we consider the CH bond, in the CH bond, carbon, still a 2.5, hydrogen's a 2.1. So our arrows are going to draw in towards carbon in the center. And because of the way that this tripod's laid out, all of these arrows, the ones that are the part that's pointing in towards the carbon, if we're just thinking about like flat level, those are all going to cancel out because they're evenly distributed. The arrows that are pointing up, the up part of it, is not going to cancel. That's going to add up. And for our carbon bromine, it's also going to be pointing up. So we do have this net pointing up that all of our arrows are doing. They're all pointing up. And so I would argue that this is probably polar, or just demonstrates some polarity. If we weren't thinking about do we have polar bonds, then we would have probably got this anyway. Looking at do we have lone pairs on central atom, carbon? Check, no lone pairs on carbon. Are all the bonds the same? No, the bonds are not all the same. All bonds equal? No. So this fails the nonpolar express, which usually for us means that it's polar, has dipole forces. You can expect them to be more clear-cut than that on exams. And then our last one, we've got hydrogen bonded to chlorine. Since we just have two things, we don't really have a central atom, so it's just, do we have a polar bond? And survey says, gestures towards the class. Polar bond, non-polar bond. Polar bond. It is a polar bond because chlorine has a value of 2.0, 3.0. Hydrogen is still 2.1. So our difference in electronegativity is 0.9. Polar bond, since it's just the one bond, that means that it has to be polar, so it has dipole-dipole forces. Questions about dipole-dipole forces? Great, so that was our second force. Our first force, dispersion forces. Everything has dispersion forces. Our second force, dipole forces, dipole-dipole forces. Polar molecules have dipole-dipole forces. And now we're going to go into our third force. Force number 3. Polar molecules that have hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen exhibit an additional or third intermolecular force called a hydrogen bond. The name is a little bit misleading, perhaps, so it's important that you make sure that you in your brain know what hydrogen bonding is talking about. It's not just a bond with hydrogen. This is an intermolecular force, meaning it's between two molecules. It's available to, or present in, would be better. Present when H bonds to fluorine, oxygen, or nitrogen. So if hydrogen is bonded to one of those three things, we've got the polar aspect along our bond between the hydrogen, the fluorine, the oxygen, the nitrogen, and now our molecules can interact with hydrogen bonding. This is our super dipole-dipole force. The reason that this is a super dipole-dipole force is that we have a large electronegativity between hydrogen and our most electronegative elements, fluorine, oxygen, nitrogen. They've got values of 4, 3.5, and 3.0 respectively, and they're small. So they can get very close to each other, which increases the strength of the dipole that forms along the bond. Hydrogen bonds are not covalent bonds. We're not talking about the covalent bonds. We are talking about hydrogen bonding, which is between molecules, and covalent bonds occur between atoms in the same molecule. Hydrogen bonds are much weaker than covalent bonds. They're like 2 to 5% the strength of a typical covalent bond. So they're much, much weaker. But that's really strong in terms of intermolecular forces. So let's look at HF since it's the simplest case. In HF, the molecule looks something like this. Hydrogen has a much stronger electronegativity value. And so when we draw our arrow, it points towards the more electronegative atom. So our negative side is going to be the fluorine side. our positive side is going to be the hydrogen side. These are partial negatives and positives. That's why we've got the lowercase delta here. That means that we've got a permanent dipole, the negative side being the fluorine, the positive side being the hydrogen, and we can get extra attractive strength. These are like really strong magnets that we're putting next to each other, so they're going to stick together better. And the dotted dashed lines are the hydrogen bonds. This would be like, instead of having Gorilla Glue all over your hand, now you've got like a scrapyard magnet on your hand instead. It's like the ones that they use to like pick up cars and stuff, right? You've just got one of those attached to your hands. And so now when the car comes driving by, you reach out and you slap your hand on the side of the car, and now you're stuck there forever, and you get dragged all the way down the highway. And you show up looking real raggedy at wherever their destination is. Hydrogen bonding can occur in methanol. Methanol contains oxygen bonded directly to hydrogen. That's one of the three conditions that we can have where we have hydrogen bonding available to us. The oxygen is going to be stealing a lot of the electron density from the hydrogen. It's bullying hydrogen. And so it's going to keep the partial negative charge. The hydrogen is going to have a partial positive charge because it doesn't really have electrons, at least not as much as it should. And because of that, we can hydrogen bond. So this hydrogen is attracted to the oxygen on a neighboring methanol. So they sort of stick together. They're going to preferentially clump up and form these hydrogen bonds. And then this hydrogen could attract an oxygen from a different molecule, and it'd be this whole sea of like little tiny magnets sort of lining up. If we look at the effect of hydrogen bonding on melting and boiling points for two compounds of similar molar mass, meaning that they have similar dispersion forces, we can see that there's a very large difference between melting and boiling point. So we're using ethane as our comparison point again. Ethane is nonpolar. So this is dispersion forces only. Methanol, on the other hand, has dispersion forces. It's also a polar molecule, so it has access to dipole-dipole forces. And it also additionally has access to the superdipole-dipole force, hydrogen bonding. So it has all three of the forces that we know about so far. And their molar masses are fairly similar, 30 versus 32. If we look at the boiling and melting points now, our boiling point for ethane was minus 88 degrees Celsius. Again, you're going to freeze, you're probably going to die, unless you've got very specialized equipment. And methanol's boiling point is 64.7 degrees Celsius. That's super hot. You would also probably die, but for it being too hot. So we've got a difference of around, is that 80? It's in the ballpark. Nope, it's not 80. 88, 90, 150. That's about 150 degrees Celsius difference by adding on dipole-dipole forces and hydrogen bonding forces. So that's more than the difference from going from freezing cold to boiling hot water. That amount of change by adding in the hydrogen bonding forces. For our melting point, it hasn't changed quite as much. It's about an 80 degrees Celsius difference, which is still a lot. It's just not as impressive as 150. So that's the effect of adding hydrogen bonding and dipole-dipole forces. They stick to each other a lot more, and so it takes a lot more energy to get them to separate, in boiling especially. Hydrogen bonding also occurs in water, so water molecules can form really strong hydrogen bonds with each other. Water is especially special because we've got oxygen bonded to 2 hydrogen molecules, so that means we can do 2 instances of hydrogen bonding. And again, these are the hydrogen bonds, the dashed lines. So the boiling point of water being 100 degrees Celsius is really, really high for something that's so small. 18 grams per mole is really, really small. And it's because of these really strong, kind of all over the place hydrogen bonds. This is if you have got 2 scrapyard magnets stuck to your hands. And now you're slap your hands on the side of a truck as it's passing by, and then they peel you off in Arizona. Hydrogen bonding shows up in biology. We have hydrogen bonding all over inside of us, partly because we have lots of water in us, but it also keeps our DNA together. So the 2 strands of DNA in the double helix pictured here on the right, are held together by hydrogen bonds. So different base pairs have access to things that can do hydrogen bonding. Nitrogen bonded directly to hydrogen shows up in a bunch of the base pairs in our DNA. So that activates the ability to do hydrogen bonding. So we can do some hydrogen bonding with oxygens and nitrogens and their lone pairs and all sorts of fun stuff. Thinking about HF and HCl, which has the higher boiling point and why? So thinking about our 3 forces, our dispersion forces, our dipole-dipole forces, our hydrogen bonding. How are they similar? How are they different? How are they similar? They both have hydrogen. That's true. They both have dispersion forces. Which one's going to have stronger dispersion forces? How do we compare dispersion forces? Molar mass. So we're looking for bigger molar mass. Which is going to have the bigger molar mass, HF or HCl? HCl. So HCl has bigger dispersion forces. Probably. What about our second force, dipole-dipole forces? Do either or both of them have dipole-dipole forces?
I think they both have dipole-dipole.
They both have dipole-dipole forces. What do we need to have dipole-dipole forces?
Polar bond.
We need to have a polar bond. So if we're looking at the bonds, hydrogen has a value of 2.1. Again, if you're looking at, if you have your yellow sheet handy, on the bottom right corner of each of the cells, you should see a value for most of the elements. And hydrogen's got a 2.1 there. That's where we're getting that value from. You can also look up a table of electronegativity values. Fluorine's the one that we should know. It's 4.0. Chlorine has a 3.0. So if we're looking at our differences in electronegativity, we've got a value of 1.9 for HF. We've got a value of 0.9 for HCl. Which of those is going to have stronger dipole-dipole forces? Dipole-dipole forces depend on the bond being polar. A stronger polar bond will have stronger forces, which has the stronger polar bond. HF. So HF is going to have the stronger dipole-dipole forces. Which is stronger, dispersion or dipole-dipole?
Dipole, dipole.
Dipole-dipole. So far, HF is winning. Stronger dipole-dipole forces. Is there another force that we have available to us?
Hydrogen bond.
Hydrogen bonding. Do either of these two meet our requirements for hydrogen bonding? HF has the conditions for hydrogen bonding. HF has it. We need to have hydrogen bonded directly to fluorine, oxygen, or nitrogen to be able to do hydrogen bonding. HF is one of those conditions, so this also has hydrogen bonding. Is hydrogen bonding stronger or weaker than dipole-dipole forces?
Stronger.
It's stronger. So which of these is going to have the higher boiling point? HF. HF is definitely going to have the higher boiling point. So HF has the higher boiling point because it has stronger intermolecular forces. So HF has a higher boiling point because it has stronger intermolecular forces, IMF. Questions so far? So again, this sort of all builds out of what we learned in Chapter 7. It's important that we make sure that we understand Chapter 7 so that we can do this stuff in Chapter 9. So why are intermolecular forces helpful? What do they do for us? The physical state, solid, liquid, gas, of a sample of matter depends on the strength of the intermolecular forces relative to the amount of thermal energy that they have. If you give anything enough thermal energy, it will either decompose, it'll break down into its atoms, or it's going to turn into a gas. If you send anything into the center of the sun, it will turn into a gas 100% of the time. It'll probably break into other things too. All sorts of crazy stuff going on in the sun. But at some point, it will vaporize. We don't have anything that can go into the sun and not vaporize. So that would be the maximum amount of thermal energy probably that we have a frame of reference for. Things at normal room temperature though, obviously there are some solids, there are some liquids here. And so those, because they have really strong intermolecular forces, haven't turned into gases yet. They're really sticking to each other. They've got magnets for hands, and they're sticking to passing by cars. As it turns out, all atoms, everything, including solids and liquids, so solids and liquids too, not just gases, are in constant random motion. They're always moving around. In the case of solids, they're stuck in their seat, but they're still jiggling and wiggling and they're doing weird stuff. In the case of liquids, they can move past each other, but they are always moving. The energy associated with that movement or that motion is thermal energy. Substances that have weak intermolecular forces don't stick together very well. And so you give them a little bit of energy and they're going to split, they're going to separate. If the intermolecular forces are strong relative to the thermal energy, the sample is likely to be a liquid or a solid. And we've got a bunch of different types of solids. So we've got crystalline solids. Crystalline solids form, any guesses? Crystals. They form crystals. So solids can be crystalline, meaning they have a well-ordered array of atoms or molecules. They form crystals. Generally, we tend to like the way that crystals look, just as like a general species. Crystals tend to be prettier than non-crystals. Or they can also be amorphous, having no long-range order. And amorphous, we're thinking like blobs, less attractive generally than well-ordered crystals. Our crystalline solids, our pretty ones, can be divided into 3 categories based on the individual units, the smallest pieces, that compose the solid. we've got molecular crystalline solids, ionic crystalline solids, and atomic crystalline solids. And we'll talk about each of them briefly. For our molecular solids, are solids whose composite units are, you guessed it, molecules. Molecular pertaining to molecules, they're molecule-based solids. Molecular solids made of molecules. So we're thinking things like ice, dry ice, both things that are nice and crunchy. And these are held together by intermolecular forces, our dispersion forces, our dipole-dipole forces, and our hydrogen bonding. Ice is held together by hydrogen bonds, our strongest intermolecular force. Dry ice, which is carbon dioxide, is held together by dispersion forces. In general, molecular solids tend to have low to moderately low melting points. Ice is one of the higher molecular solid melting points. It's not the highest, but it's relatively high. And again, high here is 0 degrees Celsius. Things that are even higher would be more like sugar, but you can melt sugar on like your stovetop. You can make caramel at home. Dry ice turns into a gas at negative 78 degrees Celsius. Generally, molecular solids have low melting points. Low to moderately low melting point for our molecular solids. We also have ionic solids. Anyone want to guess what ionic solids are made of? Metal and nonmetals, ionic compounds, yeah. So ionic solids are made of formula units made of ions, a repeating array of positively and negatively charged ions, thinking about things like table salt. Calcium fluoride would also be an ionic solid. Magnesium chloride would also be an ionic solid. These are held together by electrostatic attractions between cations and anions. Those are basically full positive and full negative charges. Those are going to be way stronger in terms of their magnet force than our hydrogen bonding. So the sodium and chloride ions in sodium chloride are going to be held together in 3 dimensions. So they're going to be held on all sides by different magnetic forces. These tend to have high melting points due to the high bond strength. So instead of partial positive and negative charges like we had with hydrogen bonding and dipole-dipole force, we have full positive and negative charges. These make for strong forces, not to be confused with the strong force. Strong forces mean high melting points. So sodium chloride, table salts, has a melting point of like 800 degrees Celsius. So if you max out the temperature on your oven and you throw salt in there, you're just drying out your salt. You're not going to be able to melt it. Your oven probably goes to 550, 650 degrees Fahrenheit, and Celsius is going to be much bigger than that. So think like 1400 degrees Fahrenheit, maybe. That's super, super high. And then our third crystalline solid is atomic solids. Atomic solids are made of atoms. And there are different types of atoms, lots of different types of atoms, as you can see on our periodic table. We can subdivide these into 3 categories, and they have different kinds of forces built into them. the type of atom determines the strength that they connect with each other. So we've got three subcategories for atomic solids with widely varying melting points. So for our atomic solids, we've got covalent atomic solids. Covalent meaning that they're connected by covalent bonds. So where it's all one chemical, like carbon makes up diamonds, but all the carbons are covalently bonded. They're sharing electrons with their neighbors, so they're bonded in all directions, and covalent bonds are really strong, way stronger than intermolecular forces, are dispersion, dipole-dipole, and hydrogen bonding. And so our covalent atomic solids, because they're bonded together with covalent bonds, these are going to have high melting points because covalent bonds are very strong. A diamond crystal is basically a giant molecule of carbon. Assuming that there's no impurities, imperfections, if it's a perfect like lab diamond, it's all carbon the whole way through. It's all covalent bonds. Diamond has an estimated melting point of 3,800 degrees Celsius, which probably your car would melt before you melt a diamond. So that's super, super high. And here's what a diamond in the rough looks like on the left. And here's what the crystal structure of a diamond looks like. The purple dots are just our corners for our cube. And then the white bits in the middle, those are representing our carbons. So they're all bonded to each other. You don't need to know anything about like the way that they're bonded together, just that they are bonded together with covalent solids or with covalent bonds, and it's in all directions. So that's our first atomic solid. We've got covalent bonds. We've got then ones that are not bonding. So non-bonding atomic solids. No bonds. So they're not going to be very sticky at all. And these are things that are held together by our relatively weak dispersion forces. We're thinking of our noble gases like solid xenon. So they're not going to form bonds. No bonds, just dispersion forces. All of these solids make for great flashcard material, by the way. So we've got just dispersion forces, very low melting points. Like helium has a boiling point of 4 Kelvin. I'm not entirely sure that it has a melting point. It's below 1 Kelvin if it has a melting point. So it's like almost no energy at all. And it's like, yeah, we're not sitting still. They're the ultimate ADHD final boss of atoms and elements. Xenon melts at negative 112 degrees Celsius. Again, you would die in negative 112 degrees Celsius. So that's our second, non-bonding atomic solids. So we had bonding, covalent bonds, atomic solids, non-bonding atomic solids. We also have metals that have their own special type of bonds. Metallic atomic solids are held together by metallic bonds. Our metallic atomic solids are the peace and love category. They're just kind of freely sharing their electrons with all the other metal atoms that are next to them, near them. And the bond strength varies wildly. On the one hand, we've got things like mercury that melts at negative 39 degrees Celsius, which is really cold. So mercury is a liquid at room temperature. On the other hand, we've got things like iron that melts at 1800 degrees Celsius. which, again, really, really hot. And here's what that metal C might look like. Our simplest model of a metal, each atom donates one or more electrons to an electron C, and the electrons just sort of float around. They're not really owned by any particular nucleus. So it's sort of this like loose field of negative charge and positive charge overlapped with each other. Very hippie vibes. All right, we've got some crystalline solids. Are these molecular, ionic, or atomic? If they're atomic, are they covalent, non-bonding, or metallic? So you and your people around you work on this for a minute or so. All right, bringing this back. That might have been a minute, I don't know. Looking at our first thing, NH3. What kind of elements do we have in NH3? Metals, metalloids, nonmetals? Yeah, one of those three. Which one? We've got nonmetals. It's just nonmetals. It's all stuff that's in that upper right corner of the periodic table. Nonmetals only, and that means that it is a molecule. Molecules form molecular solids. So NH3 is going to form a molecular solid. Meaning that it's probably going to have pretty low intermolecular forces strength. It's going to have a relatively low melting point, boiling point. How about runs batted in? What kind of compounds do we have, or what kind of atoms do we have in RBI? What's RB? Rubidium. What kind of thing is rubidium? Yeah, it's a metal. And then I? Iodine, iodine. Non-metal. So we got metal and non-metal. It is ionic. So it's going to form an ionic solid. It's probably going to have a relatively high melting point. Just based on the type of thing that it is, we could guess it's probably got a high melting point. It's probably a solid at room temperature. And then krypton, that molecular, ionic, or atomic? It is atomic. It's one element only, meaning that it's atomic. It's an atomic solid. What kind of atomic solid do we think it might be? Covalent bonding, non-bonding, metallic. Is krypton, Kr, a metal? Not a metal. Can't be a metallic atomic solid. So it's got to be bonding or non-bonding. What group is krypton in? What do we call that column? Noble gases. Do noble gases like to bond? They absolutely hate bonding. If you force a noble gas to bond, it'll do anything that it can to stop bonding. They're very xenophobic's not the right word. They're very introverted. They're not going to socialize. They're not going to play well with others. So it's atomic. It's also, if we can write, can we write? Can we write? Can we write? Apparently not. My pencil is freaking out. Apple Pencil, thank you. All right, well, I can't write anymore. I'm in timeout, I guess. So we've got one element in there. It's an atomic solid, and it is non-bonding. So it's probably going to have very low melting point because of that. Now we're going to talk about our different things, liquids and solids. In gases, our molecules and our atoms are going to be separated by distances. We spent the whole last chapter, chapter 8, talking about gases and how they're separated by distance. In solids and liquids, the molecules or the atoms are touchingly close. We've talked about this before. This is not really new to us. So they're all in contact. They're close enough that they can interact with their neighbors. And the difference between solids and liquids is just how freely they can move around. So in liquids, they can move past their neighbors. This is people at a rock concert up in the front area, not sitting back in their seats. People in a rock concert, they can move past their neighbors. They can move around each other. In our solids, that's more like people in a lecture room where you're all kind of stuck in your own spot. You can still interact with your neighbors. You can reach out and punch somebody, which you shouldn't do because that's bad. But you could do that. You could also do nice things to people around you as well. Visual of our gas, liquid, and solid states. In our solid state, notice we're not depicting really any empty space, or not much. They're all locked in, and they're also all oriented the same direction. That typically happens also in solids where they line up in the same direction, and that's what forms crystalline structures, is when they all line up in a specific formation. In the liquid phase, they're not all lined up. They can move past each other. They can rotate around. They can do whatever they want, essentially. But they're all still super close to each other. When we get to the gas phase, they're separated by space. There's empty space in there. So looking at gases, gases are going to have low density because of the empty space in there. They're going to have indefinite, meaning not set, not solid, shape, and volume. They will take up the space that they're in. They'll spread out across the room that they're in. If I had Taco Bell up here with me, for example, eventually the people in the back would probably smell the yummy or horrifying, depending on how you feel about Taco Bell, smells. They would make their way around the classroom. Everyone would be smelling that I've got Taco Bell, but I don't have Taco Bell, so you're not smelling that. So that's the indefinite shape and volume. They'll fill out the shape of their container. These are always going to have weak intermolecular forces relative to thermal energy. They're weak enough that they've completely separated from each other. Our properties of liquids, these are going to have high density compared to gases. So I'm going to say higher density because they're touchingly close. There's no empty space in there. They're going to have a definite volume. You can't compress them because they're already touchingly close. But they have an indefinite shape. So it takes the shape of the container. It'll flow downhill. If you push it, it can move around. But it has a definite volume. So the indefinite shape, definite volume, this is why hydraulic presses work. Completely irrelevant to the class, but I think it's cool. So the way a hydraulic press works, you take a large amount of liquid, you take like a giant piston. This is like just the basic concept. You take a giant piston, you push on the large surface area of water, and the water can't compress. It's already as close as it can get to each other. And so now you're just pushing on the water, and that's going to exert force on all the sides of whatever's holding it in. If you give it a tiny little outlet where it can push all that force onto, that's the part that and then like crushes things in the videos. Right? That's the little arm that's moving down. They're pushing with a giant piston, concentrating all that area over a really small force. which causes it to really hurt. This is also like if you step on a Lego. Legos are like sort of sharp, but if you're putting your entire body weight onto that small little corner of the Lego piece, it hurts a lot more. Again, completely unrelated to the class, but sort of relevant for why we can use liquids to do that. Solids, on the other hand, also have high density in comparison to gases. So we've got higher density again. These have definite shape. Definite shape is what makes solids special. They also have definite volume like liquids because they're touchingly close. We can have crystalline, ordered, or amorphous, disordered. These are going to have the strongest intermolecular forces relative to thermal energy. So liquids assume the shape of their container. The molecules are free to move around each other. And I apparently never found a picture to put in here. They can flow and assume the shape of their container, which is also why you can like drink liquids from cans and bottles. You just pour the liquid. You move it around, slosh it around, stir it up, and then it pours out. You wouldn't be able to do that if your drink is frozen, if it's solid. Solids also have definite shape. In solids, like ice, very crushable. The molecules are fixed in place, so they're sort of doing this lineup. The hydrogen bonding between neighboring hydrogens and oxygens. They're going to lock into that place if you give them enough time. And that creates really nice, optically pure ice. If you don't give it time to form into these structures, if you freeze it too quickly, it's not going to form optically pure ice. Or if there's other impurities and stuff, there's a whole art to it. Intermolecular forces also play a role in surface tension and viscosity. So if we didn't have intermolecular forces, if we didn't have these sticky forces that keep the atoms and molecules together, solids and liquids wouldn't exist. Everything would be gas, including us. So we wouldn't be here. We wouldn't be learning chemistry. We would just be gases. In liquids, we have surface tension and viscosity, which are the result of intermolecular forces, and we'll talk about those briefly. So surface tension, something that you can do with surface tension with water is you can set a paper clip. If you set it gently enough on the surface of water, it'll float there because it's light enough, and the surface tension of the water holds the water together, sort of like pushes out things trying to get in. So this paper clip is held up by surface tension, and surface tension is the tendency of liquids to minimize their surface area. If you try this trick on gasoline, which I don't recommend because you shouldn't be touching gasoline, it's not going to stay up. If you try it with like acetone or isopropyl alcohol, probably also wouldn't work because the intermolecular forces just aren't strong enough to maintain the surface tension. Surface tension exists because molecules that are up on the surface, we've got a picture here with a mosquito, SWAT. Surface molecules experience a net inward force. So if we're thinking about the water molecules inside, this lower water molecule that's got arrows in all directions, it's being pulled every which way. It's in constant contact with all of its neighbors. If we're up on the surface, though, there's nobody above us. So there's this great big sky. And we're just being held on the sides and down. So this one that's in the middle is being pulled in every direction, and so it's not being pulled really in any one direction. It's just sort of in balance with its neighbors. The ones that are on the surface, because there's nothing pulling them up, are being pulled down. So there's a little bit of a downward pulling force for any liquid. And that downward pulling force is what causes it to minimize its surface area and form droplets. This is also why if you fill up a glass of water and you like fill it up a little too tall, you can get the little like dome shape on the top of a glass of water. It's like, that shouldn't be there, but it is. And then if you have to walk with it, you're like, slurp the top off, and then you can, without spilling. So this is why water drops are spherical, is because of surface tension. So water drops in nature, or if you go up into space, this really cool picture of some astronauts in space, they've got this giant ball of water just floating up there. The intermolecular forces hold the water together, and it makes this big globe shape. I'm guessing that this is probably that's probably a relatively dangerous thing to do in a space shuttle, because I don't think you want water just flying around everywhere. So that's surface tension. That's also how like water bugs and other things can sit on the surface of the water, is because of that surface tension, and they're really light. And we'll talk about viscosity before we wrap up. Viscosity is the resistance of a liquid to flow. We can sort of think of this as the thickness of a liquid. It's not exactly the thickness of a liquid, but like that's sort of what it is. For some reason, I for a long time had viscosity backwards in my brain. The liquids that are viscous flow more slowly than liquids that are not viscous. So motor oil and honey are viscous liquids. They don't flow very well. They're kind of globby. They sort of just clump up and get everywhere. And that viscosity is because of strong intermolecular forces. It makes them harder to move around each other, so like closer to being a solid, and that hinders their flow. So if you're pouring out honey, it's more viscous because the sugar and the water molecules that are inside of there interact really strongly. You've got really high concentrations of sugar. That causes it to sort of clump up a little bit. It's a little bit more stuck together. So it's harder for the molecules to move past each other to flow out and pour. If you heat it up, you give it more thermal energy. Now it can move faster, and so it pours more easily. Any questions so far on intermolecular forces? Remember, dispersion forces, dipole-dipole forces, hydrogen bonding.